Welcome back everyone to MATA35. In this lecture, 8C, we're going to be talking about numerical solutions, so Euler's method and Runge-Kutta. So the first thing we're going to do is recall that when we had Riemann sums. So for any integral problem, we can approximate it with lots of little rectangles, and the approximation gets better the more rectangles we have. So if you had x, y here, let's say you had some starting point. Let's say this is a is equal to x naught, and some b is equal to xn. And you had some curve that you're trying to get the volume under. Well, then maybe what you do is you take this rectangle. You can just take a bunch of these little rectangles. Each of these having delta x size, and then your integral. So let's say this function is f of x. Then your integral f of x dx from a to b is approximately equal to the signed area in rectangles, which is equal to this sum from I equal 1 to n of delta x times f of xi. Okay, so that was one of the ways you can numerically compute an integral. Now, let's remember when we're thinking about ODEs, we had these direction fields, and they tell you which direction the solution goes. And so we can approximate a solution to an ODE by starting somewhere and following the direction field in lots of little steps. So for example, if we started, let's say, up here, you might follow it along for this far, and then follow that along this far, and then follow this along. So basically what we're doing is we're taking a direction of the direction field, and then we're jumping forward some set amount of distance along the x-axis as you're going along each of the steps. But now note that, of course, this is not going to be smooth, and it's not going to quite get the right thing, because we're sort of making these big jumps. Sometimes it's a little bit easier, so sometimes the jumps do actually correspond to a line. So we're following the direction field, but of course we don't know the direction at every single point. We have to follow along for some distance, and then we can recompute the direction. And this gives us one simple way of figuring out a solution based on an initial value. And so this is called Euler's method. So suppose we have an initial value problem. Y prime is equal to some function of x and y, and y of x naught is equal to y naught. What we can do is we can choose a step size, delta x. Let me write out an example here, actually. Yeah, come on. So let's say we had y prime is equal to x plus y, which is fairly easy. And let's say we started out at y of minus 1 is equal to 0.5. And let's say delta x is equal to 0.5. So we choose a step size. Then what we do is we let x sub I plus 1 is equal to xi plus delta x. So x naught here is equal to minus 1. Let's say x1 here is equal to minus 0.5. x2 is equal to 0. x3 is equal to 0.5. And x4 is equal to 1. So these are the points where we're going to evaluate our function. So if you think about these are sort of like the endpoints of the rectangles for the Riemann sums. And we also had that y naught is equal to 0.5. So let me draw this out. So let's say this was 0.5, this was 1, minus 0.5, and let's say this was minus 1. And let's say we're starting, this is 0.5, and this is 1. So what we know is our solution starts at minus 1, 0.5. So our solution starts there. Well, then what we want to do is then we want to figure out where it is next. And so the way we do that is we compute the value of f of xy. So we compute the slope at this point. So we can compute the slope at this point, which is going to be, let's see, let me actually give myself a little bit more space here. So let's say this is y is equal to 0.5. And so then we want y naught is equal to 0.5. And so then f of the slope here, f is going to be equal to minus 0.5. And then for the next point, you just sum all those things together. So if y1 is equal to, if y0 is equal to 0.5, then y1 is equal to 0.5, where you were, plus the slope, so that's minus 0.5, times the step size, 0.5, and that's going to give you 0.25. So that's there. Because what we did is we looked at the slope here, and then we continued along it. So let's say if this was the slope, we're going to continue along this line until we get down to as far of a step as we're taking. And our step size is 0.5, and so we're going from minus 1 to 0.5, and we're taking a big step. And then the next thing we're going to do is then we're going to take so then we need to figure out what f is. Well, so what's the slope at 0.5, 0.25? Well, y prime is equal to x plus y, and so the slope here at this next point is going to be minus 0.25. Okay? And so if the slope is minus 0.25, then y2 is going to be equal to 0. Our point was also at 0.25, plus minus 0.25 times the step size, 0.5. That's going to give you 0.125. So that's going to be 0.125 as we go there. And we can keep on going. So let's do a couple more steps. So then we have y3 is going to, so we need to compute the slope at that point. That slope there is 0.125 because it's 0 plus 0.125 by, since our slope is x plus y. And so then y3 is going to be equal to 0.125 plus positive 0.125 times 0.5, which is going to be equal to 0.1875. So now we're starting to go back up. 0.1875 is slightly up. So we go there. And lastly, for our final step, we have y4 is equal to 0.1875 plus, well, what's the slope there? The slope here is 0.6875. So 0.6875 times 0.5. And so that's about equal to 0.53. So that's going to get you back up here. So what we're doing is we're taking a series of finite steps. And so we're asking, at every point of our solution, we're asking, well, at this point, what is the direction that I should be going? I look in that direction, and then I take a step of a particular size in that direction. And the rub of it all is that the y-ends are approximately equal to y of xn. So this isn't going to be exact because you're taking these big steps instead of doing it continuously, but you still get a reasonable approximation. And the sort of intuition for why this works comes from the idea that if you rewrite this equation, this is y of I plus 1 minus yi is equal to f of xn yn delta x. So you'll notice that this, if we call this delta yi, that's it's equal to f of xn yn delta x. And so this is similar to saying, if you take the limit as, how do you get f, if you take the limit, this is just f is equal to f of xy dx, which is our original equation. So basically we're taking our original equation, and then instead of using dy and dx, we're replacing them with delta x and delta y, where our delta y is given by this formula. How do you get f, and what does it represent? So if we had some equation y prime is equal to x plus y, then f of x y is equal to x plus y. So that's just the formula that gives you the slope. So f is the slope, yeah. Because remember, our direction fields, which is what we have here. So in this particular example, we use the computer to compute the direction field at every single point. So then we can just follow it along, right? Now the problem is that, how do we compute the direction field? Well, we look at the slope at every point. And the slope is just what y prime is equal to. And so the slope here is x plus y. If you haven't computed the entire direction field, because that's very expensive, you might only compute the direction field or the slope at particular points along your solution. So you just follow each of the directions along the solution, and it gives you an approximation of the right answer. So basically, we have this direction field, and I'm just saying, well, it's too expensive to know exactly what the slope is everywhere. So instead, I'm just going to take finite steps and then recompute my slope after moving a certain amount of distance. Okay, so now that you roughly know Euler's method, let's try it out. There. So consider y prime is equal to y, where y of 0 is equal to 1, and estimate y of 1 using Euler's method with the following step sizes. So let's say delta x is equal to 1. I'm going to go ahead and get started on this first one for you. So here we know that x naught is equal to 0, and y naught is equal to 1. What is f of x? So f of xy is equal to y. So the slope is just equal to y, so it's just their y point. So then what's the slope at this very first point? So the slope here is going to be equal to just y, so that's just equal to 1. How do we know that y prime is equal to x equal y? I'm not sure what your question is. Oh, x plus y. Oh, that is given to you. So basically, I give you a differential equation. So I give you a differential equation, y prime is equal to x plus y, or y prime is equal to y. And then you're trying to find solutions to this differential equation. So that's the whole point of the problem. So right here, the problem is y prime is equal to y. So what is, and we know that we have a solution that passes through y of 0 is equal to 1. So now we're plugging in f of xy is equal to y, and y of 0 is equal to 1. But anyway, so let's do this very first one. So what do we get? We get x1 is going to be equal to, well, it's going to be equal to the previous value, which was, x1 is equal to 1 because the previous value was 0 and their step size is 1. So then y1 is going to be equal to, well, the previous value, which was 1, plus the slope times the delta x. 1 times 1 is equal to 2. Okay, so that was the very first one. So that was C. But now I'm going to ask you to do a smaller step size. So if the step size is 1/2, what is the value, what is your estimate of y of 1? Okay, so we have a B and A, E, B, E, B, 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 E, B, B, E. Okay, so it's somewhat split between B's and E's. So let's take a look. Let's actually solve it together. So we have x naught is equal to 0, so x1 is equal to 1/2, and x2 is going to be equal to 1, right? Because these are our step sizes. So we start at x0, and then we take one step and we're at 1/2. We take another step and then we're at 1. And we know that y naught is equal to 1, so that's just by initial start. And of course, we know that f at 0, 1. So remember, f is a function, so you're evaluating at these 2 points. That's just equal to y low, so that's equal to 1. So then y1 is going to be equal to 1 plus 1 times 0.5. So that's going to be equal to 1.5. y2 is going to be equal to 1.5 plus 1.5 times 0.5, which is equal to 2.25. So the answer here is actually C. Did everyone understand that? A lot of people got B for this answer. Oh, okay, yes, so it looks like we had a bit of confusion. So what we're looking for is y of 1. Yeah, okay, so thank you for bringing this up. This is actually quite confusing. So you have some function. The solution is some function y of x is equal. Let me actually solve this equation for you to make it a bit more obvious. So so we have y prime is equal to y. That is our actual equation, right? Y prime is equal to y, and so therefore dy dx is equal to y. So use separation of variables. Dy over y is equal to dx. Natural log of y is equal to x plus c. And so y is equal to some constant times e to the x. When you plug in y of 1 is equal to 0, you end up getting that y is equal to e to the x. Okay? So this is the actual solution. So this is actual solution. Is y is equal to e to the x for this entire function. Oh, how does the c come out in front? So, okay, let me go through this step by step. So this implies that y is equal to, the absolute value of y is equal to e to the x plus c, right? But now this is equal to e to the x times e to the c. And so we can have a different, but this is just some arbitrary constant, right? And so this implies the absolute value of y is equal to some constant, c2, e to the x, where c2 is equal to e to the c. But you can just replace c2 with c, since they're all just some arbitrary constants, and so we don't need to keep track of the fact that it's a c2. But of course, this is some arbitrary constant, and so we're taking the absolute value of y is equal to some arbitrary constant. So that means that y is equal to some constant times e to the x, because it just comes out in the constant again. And then you solve for y of 1 is equal to, y of 0 is equal to 1. So that means 1 is equal to c e to the 0, which implies that c is equal to 1. And so then this gives you this formula here. Okay? Sorry. Let me move myself away for a moment. Okay, so that's basically that is the actual solution of the problem. So this is just solving it using as a separable ODE. You can also solve it as a linear first order or whatever, but this is a separable ODE, and so we solved it that way, and you get y is equal to e to the x for the actual answer. But now that's the actual answer, but sometimes solving the actual ODE explicitly is hard, and so what we're doing is we're approximating it instead. So what we're trying to do is we're trying to find out at the point x equal to 1, what is the value of y. So in the very first example here, we took a single step. We started at x is equal to 0, and we took a big giant step over to x equal to 1. And so therefore, the first y value is the value at y of 1. But now over here, because our step size is smaller, we had to take 2 steps to get there, right? We started at x0 is equal to 1, x1 is equal to 1/2, x2 is equal to 1. And so that means we take 2 steps. And so that means the corresponding y value is y2. And so that's why the answer to this is 2.25. Okay, let's try it again. So let's say we have the step size is 1/3 instead. So let me go ahead and give you the setup to make sure we're all together. Yeah, so y1 is, so x1 is 0.5, and therefore y1 is y of 0.5. So let me write that. So this one here, y1 is equal to y of 0.5, approximately. Yeah, so this was a question of indices. So let me give you a little bit more information on this next one. So x0 is equal to 0. x1 is equal to 1/3, x2 is going to be equal to 2/3, and x3 is going to be equal to 1. And so then y0, which is approximately equal, I'm going to run out of space, but hopefully this won't be too bad. So y0 is approximately equal to f of let me give myself a bit more space. So let's say y of 0 which is approximately equal to y0, y of 1/3, which is approximately equal to y1, y of 2/3, which is approximately equal to y2, and then y of 1 is approximately equal to y3. And we know that this happens to be equal to 1, and that's by assumption. And we know that the initial slope is also equal to 1. And let me go ahead and get you started. So y1 is equal to 1 plus 1 times 1/3. So that's equal to 4/3. Which is approximately 1.3 repeating. And so here, it turns out that y2 is going to be equal to 4/3 squared, which is approximately equal to 1.7 repeating, and y3 is going to be approximately equal to 4/3 cubed, which is approximately 2.370 repeating. And so the answer here is B. Okay, does everyone sort of understand what's going on? So you have some algorithm here for Euler's method, and what you're doing is you're just taking little steps. You're taking lots of little steps until your x value gets to whatever value you're looking for. Once your x value gets there, then the y value at that point is approximately your answer. Okay, but of course you'll notice that for each of these different step sizes, we had a different. Would we get to use a calculator? It makes sense though, I just don't know the decimals. I will, if I give you an, let me actually look to see what I gave you on the practice quiz. I think I gave you a relatively easy one on the practice quiz. So, yeah, so on the practice quiz, I will give you numbers that work out nicely without decimals. Or sorry, on the actual quiz. So like, if I designed this question correctly, and I need to double check it, you shouldn't need to use any decimals for this problem. So I will design the problem so that you can just add things together. Okay, so now where were we? So you'll notice that the different approximations all have errors. So our actual answer is y is equal to e to the x. So y of 1 is actually equal to e, which is approximately 2.718, right? So the actual answer is e. But each of our approximations, as our step sizes got, for the step size of just one big jump, that was pretty bad. We got an approximation of 2. When we had 2 steps, with each of the smaller step size of 1/2, our approximation was better, and we got 2.25. When we had three steps, we had 2.337, and so on. So as you have more and smaller steps, you end up more closely approximating the actual solution. So now, of course, if you had infinitely small steps, so then you might call delta x dx instead, well then that gets you back to solving an integration problem. Okay, but so this is one of the issues with Euler's method, which is that there are errors with the approximations. So we only use the slope as a starting point, and errors can accumulate. At the starting point of the integral, and the errors can accumulate. The smaller the step size, the more accurate the approximation, but it also requires more computation time. So for example, suppose that we had an actual solution. Let me see if I can draw an actual solution. So let's suppose that this is an actual solution in the red line here. Well, what happens when we take a big step? So if we take a big step all the way to 0, following along that line, you'll notice that our approximation gets bad pretty quickly. So if we're here and then we take another step there. So this is not a great approximation if our step sizes are too big. On the other hand, if we take slightly smaller step sizes, let's say we took a step size to here and then took a step size to there. So if we take more step sizes, then our approximation is better. And as we take more and more step sizes, you do get closer and closer to the right answer, but you'll always end up with some amount of error because the problem is that the slope changes over time. So as the x variable is changing, the slope is also changing. But we're taking this big jump along where we aren't recomputing the slope. And the more steps we take, the more often we recompute the slope, and so the lower the error. But now, you remember we had a similar problem when we were dealing with integrals, right? And so the problem with integrals is we were taking just a big rectangle, and the height of the function could change as along that rectangle, and so the rectangle had some amount of approximation error. How did we solve it? Well, one of the very first things we learned in class was the trapezoid rule. So we can reduce the error of an integral by using both endpoints of the integral of an interval. So, if we have some function here, and if we draw a bunch of endpoints, well, one thing that's significantly better is instead of taking these rectangles, which have a lot of error, instead we can use trapezoids. And so then their error is much decreased. And here we still have our starting point A, starting endpoint B is equal to xn, this is equal to x naught, this is x, this is y, and this is a function f of x. And even with these bigger intervals, our delta x, our error in the approximation is a lot closer. So this was a trapezoid rule. So what we're saying is the area, the integral of f of x dx between a and b was approximately equal to the area in the trapezoids. And we gave an explicit formula for that, which was the sum over I equal 1 to n of 1/2 times delta x times f of xi plus f of xi minus 1. Okay, so hopefully you guys remember the trapezoid rule. Basically, if you take additional points to try to figure out the, you can sort of think of this as a better approximation of the slope of the function by using these two endpoints. So by using both of the endpoints, you get a better approximation of the space as the function changes. So this leads to an idea of the Runge-Kutta family of methods. So these are a series of a bunch of different methods. In fact, you can call Euler's method first order Runge-Kutta, but since it only uses a single point, it uses the slope at a single point to figure out where to go. Higher order methods use multiple points to derive a better slope. So let me give you some intuition. So the intuition we have here is that if we have some point x naught where we're starting, and we're trying to get to some point x1, if you have a function that looks like that, well, between x and x1, let's say this is f of x. Well, what Euler's method would do is it would take this point, and it would just extend this out. So this is Euler's method. Now, the intuition behind the Runge-Kutta family of methods is that if you happen to know the slope, if you just compute the slope at this midpoint, so let's say that's the slope, you take that slope and you draw out instead. That gives you a better approximation. Let me draw that better. So note that it's still not exactly right, but this is the guess using slope at midpoint. Let me write. Guess using the slope at the midpoint of, so this is let me not call that function f of x, actually. Let me call this function y of x, just to keep my notation consistent. So this is the slope at the midpoint. So that is the basic intuition here, because that was our slope at the midpoint, and now we're guessing based on that instead of the slope at the very beginning. So now, I'm going to ask you, come on. What is the biggest problem with the intuition on the previous slide? So is it A, we don't know where the midpoint is? Is it B, we know where the midpoint is, but we can't compute the slope there? C, we know where the midpoint is, but its slope is not always a good estimate of the true slope? D, computing the midpoint takes a lot of computation? Or E, none of the above? Okay, so we're getting a lot of pretty good answers. We have a lot of C's, a few, let's see, we had an A. Let's see, what else did people put? Okay, so yes, it is actually absolutely true that we know the slope is not always a good estimate at the midpoint. It's not always a good estimate of the true slope. But this is actually not the deepest problem. The biggest problem here is we don't actually even know where the midpoint is. So if you look back here, I used the slope at here, so slope at midpoint. But we don't know this function. This is unknown. That's what we're trying to compute. So we don't actually know what the function itself is, and so because if you knew it, we wouldn't have to use any of these methods. So the problem is we don't know where the original function, and therefore we don't know where the midpoint is. We know where the midpoint is in terms of x coordinate, but we don't know where the midpoint is in terms of y coordinate. So the biggest problem is actually that we don't know where the midpoint is in terms of x, y. So it's not even that we can't compute the slope there, it's just that we don't know where it is. And this is a secondary problem. Even if we knew where the midpoint is, it's not necessarily a great estimate, but it turns out that it's usually a better estimate than the slope at the very beginning. So these are a couple of the different issues. Computing the midpoint, and you might ask, well, how do you compute the midpoint? And the answer is we can try to approximate the midpoint using these same sorts of techniques. And so that brings us to, why is it better than the beginning? So the answer to that is that it's not always better than the beginning, but it has to do with the smoothness of your function. And so if your function is smooth, chances are that it's likely that your slope at the middle is better than the slope at the two sides. As we'll see later, the real answer that people use in practice is they use some average of the slope at the beginning, the midpoint, and the end. That's what people actually try using, because you don't want to always only choose the midpoint either. But yes, so it's not always. It is true that's not always a good estimate. But it's even more true that the midpoint is hard to compute to begin with. And actually proving these things is somewhat difficult and requires some assumptions on how smoothly the function curves. Okay, so let's give a naive second order method. So let's give the intuition. No one uses this method in practice. I'm just using this to give you some intuition for what we're trying to do. So naive, no one uses this. So now if we had the same, let's see, where were we? Let me see if I can draw the same graph. I probably won't be able to. So I'm just going to draw that. Hopefully it's close enough. And then what we did is, what we can do is we can use the slope at the start. So we use Euler's method. Which would give us this guess here, right? But instead of using the Euler's method to guess, we use Euler's method to compute the midpoint. So we compute the midpoint here, and then we use the slope at the midpoint as an estimate of the true slope. So note that the slope at the midpoint isn't, slope at guessed midpoint. So note that the slope at the guessed midpoint also isn't correct. So that is not equal to the actual slope at the midpoint. So the actual slope at the midpoint might be slightly off. So it's not actually equal to the actual slope at the midpoint, but it gives us some guess for it. And so that gives us the naive second order midpoint method. Yes, the guessed midpoint of the blue line. So the blue line is our guess for the function. One guess for the function using Euler's method. And so what we do is we use Euler's method to guess the midpoint, and then we look at the slope of at the midpoint, and then use that instead for the original line to begin with. And so that's our second order guess. So putting that all together, what we're basically saying is we have some initial value problem, we choose some step size, so per usual, we let k1 be equal to the f of xi, yi. So this is the slope at starting point. And then we get k2. This here is the slope at the guessed midpoint. Because this thing here, that is the guessed midpoint. Guessed midpoint based on k1, which is the slope at the starting point. And then we estimate using slope at guessed midpoint instead. Yes, so we have the guess of the midpoint. So we have the slope at the midpoint of the guess, and then we use the slope at the midpoint of the guess to guess the slope of the function to begin with. And for complicated reasons, if your function is sufficiently smooth, this turns out to, on average, be better. Now, no one actually uses this because there are many different, you can come up with all sorts of functions where this fails miserably. So for example, if you had some function that looked like this, then the slope at the midpoint is actually not good because and the slope at the start might be better. So you can come up with all sorts of cases where this doesn't work. So that brings us to a classic Runge-Kutta. So this is the actual Runge-Kutta algorithm. It's a fourth order method. So what we do is suppose we have an initial value problem. We choose a step size. Then we get the slope at the start. So this is the slope at start. So that's k1. We have k2. This is the slope at guessed midpoint based on k1. And then you do it again. So this is the slope, k3 is the slope at guessed midpoint based on k2. And then you do it again. And this time, instead of guessing the midpoint, we're going to have the slope at endpoint. So we're going to try to look at the slope at the endpoint. Slope at guessed endpoint based on k3. And then once we have all these things together, we're going to now take a weighted average of all four slopes and use that to predict the final endpoint. So you're basically taking the average of a bunch of these slopes. Because you're right, the midpoint isn't always better than the first point or the endpoint. And so this method, classic Runge-Kutta, uses a weighted average of all four slopes, which is why this is a fourth order method. Okay, so I will not expect you to do Runge-Kutta by hand. You would just use a computer to do that. If I expect you to do anything, it will be an example of Euler's method, which is just using the slope at the start, rather than doing this iterative process of guessing the midpoint, guessing the slope at the midpoint, guessing the slope at the midpoint based on the previous guess, etc. So you can even think of higher order methods where you guess the midpoint based on the previous example over and over and over again. But it turns out this fourth order Runge-Kutta is pretty good in practice. And so this and its generalizations are often used by numerical packages like MATLAB to solve ODEs numerically. And so just a few concluding remarks, since I'm running out of time, and I'm definitely not going to get to lecture 9a today. So like integrals, solving ODEs explicitly is often hard, and sometimes you don't have closed form solutions. Like integrals, solving ODEs numerically is much easier since we can approximate by taking lots of tiny delta x steps. in some sense, Euler's method is similar to Riemann rectangular sums, since you're basically just taking a single point, using that endpoint to guess the value along the entire thing. Runge-Kutta, second order, is similar to the trapezoid rule, where you make use of the average of the slope at the midpoint, basically. So it's not the same, but it's similar. It turns out that the fourth order method is actually the same as Simpson's rule of thirds, which was one of the advanced numerical methods that I briefly mentioned when I was talking about numerical integration. And in practice, we oftentimes solve complicated ODEs using Lee's and other approximations. And that ends this section. So that ends the section on numerics. And next, on Friday, when we come back, we'll start talking instead about higher order ODEs and how to solve those. So I'm going to end the recording now. Any questions?